In this video, we will learn about a class of organic reactions that fall under the term nucleophilic addition to carbonyls, where basically a nucleophile is going to react with the pi star orbital of a carbonyl, thus breaking the pi bond of the carbonyl and creating a new nucleophile to carbon sigma bond. Before we think too much about the actual reactions themselves, it's worth thinking about the structure of the carbonyl just to understand some of the different outcomes of the reactions that we'll see. So there's a few different views we want to be able to take on the carbonyl. The first is the resonance or valence bond theory inspired view, and that's the view that tells us that the carbon of the carbonyl has a bit of partial positive charge on it, while the oxygen of the carbonyl has a bit of partial negative charge on it. From a molecular orbital perspective, the carbonyl bond can be viewed this way as the overlap of the atomic carbon 2p and the atomic oxygen 2p orbitals, and in doing so creating a pi CO bond and an empty pi star CO bond. These orbitals look like this as shown. So the big thing to take away here is that there's much more volume in the pi bonding orbital around the oxygen atom, and in the pi star antibonding orbital there's a lot more volume and thus more potential for overlap around the carbon atom. And so when we're thinking about carbonyls, we want to have a few pieces of intuition here. When I say intuition, I don't mean that you should just know this automatically, but rather that I'm telling you this and this is something you want to keep in mind. So the first feature of carbonyls is that they tend to have very low pi star energies. So that makes them very good electrophiles. Because this pi star is low in energy, that's a good place for other electrons to go into. If we're thinking about where that carbonyl functional group is electrophilic, well, it's electrophilic at carbon, and we can explain that two ways. So the first way is to use valence bond theory and say that the electrostatic attraction should be at the carbon because all of our resonance tells us there's positive charge at the carbon. And the second reason we can say that carbon is electrophilic is because of that increased surface area for overlap, according to molecular orbital theory. A third thing to keep in mind that will become more and more relevant as we learn more and more about different types of reactions: carbonyl pi bonds, so the pi bonding CO molecular orbital, that one is very low in energy, relatively speaking, and so then this is a bad nucleophile. We essentially never see carbonyl pi bonds acting as nucleophiles. Finally, the way that the pi star orbital is shaped is not vertically straight up and down the way that the normal kind of atomic p orbital would look, but rather it's a little bit skewed here, and that's significant and results in what's called a Bürgi-Dunitz angle for optimal attack or overlap. And so what we see in actual reactions is that the reactants will collide at this angle up here. Rather than being completely orthogonal, they'll kind of come in from the side at this slight 107-degree angle to the plane of the carbonyl. This is not too significant in simple molecules, but as molecules get larger and more complex and crowded on the left side over here in this drawing, then that can really change how fast a reaction can go. So for all the types of reactions we learn about, we'll be very interested in the mechanism for those reactions. And so for all carbonyl addition reactions, they're going to follow a generic mechanism. And all of these mechanisms will result in the formation of what's called a tetrahedral intermediate. So I have that shown here in my generic reaction. So a nucleophile reacting with a ketone, that forms this new species, a tetrahedral intermediate, where we're thinking about the carbon atom having changed from being tetragonal planar to being tetrahedral. This is also considered an intermediate because the vast majority of the time this is not stable enough to isolate. What we actually isolate is something else. So during the reaction, maybe this process happens, you form the intermediate. The intermediate either immediately reacts to form something else, or it sits there until we try to isolate, and at that point of kind of experimental isolation, then it turns into something else. The arrow pushing for the mechanism looks like this. So I am looking at the lone pair of the nucleophile as the reacting pair of electrons. That is attacking the carbon of the carbonyl. That then causes a pair of electrons on the carbonyl to get pushed out of the way onto the electron sink, which is the oxygen. Before I go through and label everything in the product here, it's good to make sure we have everything drawn in on our reacting atoms. And it looks like now we do. That allows me to point out that this is our new sigma bond, and we've put a lone pair onto the oxygen. And so overall, this is the arrow pushing mechanism for addition of a nucleophile to a carbonyl. It turns out that this reaction is actually often reversible, and so the tetrahedral intermediate here can undergo the reverse reaction and reform the nucleophilic species and the carbonyl. That process is called a beta elimination mechanism, and it's a very common type of mechanistic pattern that will show up in many different reactions. What that looks like is like so. So I've just flipped around my reaction. So I've made the tetrahedral intermediate on the left here and put the nucleophile and carbonyl on the right. And I've also turned the reaction arrow into an equilibrium arrow. But the reaction looks like this. So I'm going to take my reactant, put in all my electrons to keep track. And what I'm going to get is that the exact reverse process. So I get a lone pair from oxygen, kind of flowing over to become a pi bond between carbon and oxygen. Then I get the pair of electrons that is in the sigma bond between the nucleophile and the carbon atom there. That is going to leave, that's getting pushed out of the way. And in this case, my electron sink is the positive charge on this nucleophile. And so in the end, what I end up with looks like this with the nucleophile and two lone pairs on the carbonyl. So here, just to summarize what's happening in a beta elimination reaction, this is going to be the general term we use for a case where we see a pair of electrons I use the term collapse down to form a pi bond, at the same time breaking a sigma bond by pushing that sigma bond out of the way. That's only made possible by the fact that there is a group that leaves, and we call that the leaving group. In this case, this group right here is our leaving group. This generic mechanism is great, but as I was alluding to earlier, this is actually not what you're going to be able to isolate if you're in the lab doing this reaction. You actually isolate something else. And so when we consider that aspect of things, then we come across some more mechanistic detail that's worth going through. The issue is that depending on the specific reaction conditions we use to perform our nucleophilic addition to the carbonyl, a different pathway will be followed. We can categorize these different reaction conditions by alluding to acid-base chemistry. So the first reaction condition we'll consider is that which seems very neutral. And so under a neutral reaction condition, we have nothing very acidic and nothing very basic in our reaction mixture. To look at these different reaction conditions, we will consider a type of nucleophilic addition to carbonyls, specifically called the hydration of ketones and aldehydes, in which a molecule of water is our nucleophile and it's attacking a carbonyl, overall creating what's called a hydrate here. Because overall what you're seeing is that the entire molecule H2 and O are adding to the chemical formula of the electrophile in the product. Mechanism looks like this. And we start off with the nucleophile and our carbonyl. So we'll draw all that in. We'll get a nucleophilic attack like so, pushing a pair of electrons out of the way onto our carbonyl, which originally has those 4 electrons. That gets us to this product here, where we can see the positive charge on the oxygen of the water nucleophile and the negative charge on the electron sink of the carbonyl. Because in our reaction, I showed you that the final product has no formal charge in it. It actually looks like, well, it seems to be 2 alcohols, but really it's called a hydrate as a functional group. Then we need to do an additional step to get to that point. And this step is an acid-base reaction because what we're getting is an acid on the left here and a base on the right. And overall what we see is that this hydrogen is kind of jumping from one side to the other. So that is often just simply referred to as a proton transfer reaction. And we usually don't bother drawing out the mechanistic detail and the arrow pushing for this because there's multiple ways that this can happen. This can either happen intramolecularly by just having the proton kind of jump from one side to the other, or it could be that 2 of these molecules run into each other just by chance, and then so they kind of pass their protons to each other. Or it could be that this molecule runs into another molecule of water in the reaction and does this intermolecular acid-base reaction. The point is that there's enough possibilities that we don't actually know, and so we just generically call that a proton transfer. So then if we're looking at this mechanism, under neutral conditions, addition to a carbonyl proceeds by first nucleophilic addition, and then second, a proton transfer. I think it's also helpful to view this in a reaction coordinate diagram. So what we're seeing is that we're starting here, in our reactants. When we perform our initial nucleophilic attack, we are creating an intermediate, the tetrahedral intermediate, that is higher in energy than the reactants. And that should make sense because we have two formal charges now in our molecule. And once we do our proton transfer to eliminate those formal charges, then we are going down a little bit in energy. Something that you'll see here is that I have my reactants drawn as being higher in energy than the products. We'll come back to this point, but this is an intended increase in energy overall. Now let's consider the acidic reaction condition in which we use acids to make the carbonyl more electrophilic. So an example of that would be to have water as our nucleophile, a generic ketone here, and a little bit of HCl in our reaction. Overall, that gets us to the exact same product, the hydrate, but it's going to happen through a different type of process. So in our mechanism, the first step is going to be an acid-base reaction between the carbonyl lone pair and the acid of the HCl. So that looks like this, where we can draw in our lone pairs. We get our acid-base reaction like so, getting us to the protonated carbonyl, which is a very electrophilic species. Once we have that, then what we can do is to react this protonated carbonyl with a molecule of water. That's going to follow the same type of arrow pushing as we saw under the neutral reaction conditions, like so, getting us to now, if we're looking at this, the water molecule is showing up on the left in our hydrate, so it's a protonated alcohol. And on the right, instead of a negatively charged oxygen, because in our mechanism we first put a proton onto that oxygen, now in the tetrahedral intermediate, it's neutral. An important piece to remember is that the chloride anion from the HCl has to still be present, right? So that's there to charge balance. These are called spectator ions, and often organic chemists will forget about these or just leave them out, either to save space or just to save time. And so we're not quite yet at the final product of our reaction as initially shown. So we need to deprotonate this position right here to get to the hydrate. And the way that happens, on paper at least, what we'll do is you use our chloride anion as a base and deprotonate the hydrogen, making HCl again. So then overall, again, we have three steps: protonation, nucleophilic addition, and then deprotonation. 1, 2, and 3. I think it is valuable to look at the energy diagrams for this other mechanistic situation, so acidic conditions, so I have that drawn out here. If we're thinking about the steps now, then it would be like so. And so if we're looking at this, what we see is that after step 1, we've entered the protonated carbonyl. Step 2 involves the nucleophilic addition. Step 3 is the deprotonation. Overall, I'm showing step 1 and 3 in the relative energies the way they are because I'm thinking about pKa's. Here, the acid-base reaction is between HCl and the carbonyl oxygen as the base. So that means the conjugate acid is the protonated carbonyl. So I'm comparing pKa's here. And when I do that, what I find is actually the stronger acid is the HCl, which means that it would be a favorable acid-base reaction in this first step. And if it's a favorable acid-base reaction, we should be going downhill in energy. Conversely, as we get to step 3 now, what we're doing is an unfavorable acid-base reaction because we are making HCl, which is a very strong acid and is a lower pKa than the protonated hydrate. And so that's why overall I'm showing you again this increase in energy. So the point there is that depending on the identity of the acid in your acidic conditions, the relative energies of all these species will be different, and thus the relative side of the equilibrium that everything lies on will also be different. Finally, we have logically basic reaction conditions as well, and we call anything in which there's a very strong nucleophile to be under basic conditions. What this looks like is something like this, where instead of now water as our nucleophile, we're thinking about something like hydroxide or OH- as our nucleophile, still getting us to the same products. The mechanism is going to look like this. So whenever we have alkali or alkali metal, alkali earth ions, then we can think about those as being charge separated here. So we do have hydroxide as a OH- species. That is our nucleophile. So I'm going to go in and fill in my electrons just so we can keep track. And what we'll get is an attack, and then pushing that pi bond out of the way. That is that nucleophilic addition process that gets us to a tetrahedral intermediate now, where unlike the previous two intermediates, I have only a negative charge on this oxygen and a neutral nucleophile that's come in, because the nucleophile started off as being formally negatively charged. During the reaction, it shares its electrons and thus becomes less negative or becomes neutral. As drawn, the reaction can only get to this point because we would need an acid to protonate this oxygen right here. One way that we could have protons available to protonate that site would be to say that we're running this reaction with a little bit of water present. So I've kind of ignored the concept of solvent so far, but let's say the solvent was water in this reaction. If that were the case, then you could have some water serving as a source of protons. That would let you do a protonation to get to the hydrate as drawn. In a reaction coordinate diagram, we get a reaction that looks like this now with two steps, those being the 1 and 2, corresponding to step 1 and 2. And what you see is that, again, we're going from a lower energy situation at the reactants. We are always increasing in energy once we do that attack and form a tetrahedral intermediate. That's always an unstable intermediate species. And here I'm showing a downhill process, although not by much. It will depend a little bit on the specifics of where your proton is coming from for the final acid-base reaction. And so a common pattern that we'll see is that different types of reactions with different functional groups can have analogous behavior depending on how similar those functional groups are. So alcohols will tend to react very similarly to water, and they will do it like this. So methanol reacting with a ketone can get you to form what's called a hemiacetal, so one OH, one what looks like an ether. That same reaction can also form what's called just an acetal, or sometimes in the literature you'll see the word ketal. And what's happening here is that overall we're getting two molar equivalents of the nucleophile, attacking the carbonyl and getting you to an acetal product. So I want to take a moment to just compare those three reaction conditions again, those three types of mechanisms, and just point out what is changing. So I have these here again, neutral, acidic, and basic. And what I've highlighted is where the reaction is right before the nucleophilic addition step. So in the neutral situation, we have neutral water as a nucleophile, neutral ketone as an electrophile. Under acidic conditions, we have neutral water as a nucleophile, positively charged or protonated carbonyl as the electrophile. And under basic conditions, we have negatively charged nucleophile, neutral electrophile. The type of thinking we want to do is to consider what has changed under the reaction conditions relative to the neutral or unaffected reaction condition. So under acidic conditions, our electrophile is much more electrophilic. It's much less stable because now it's a positively charged carbonyl that's been protonated. And so the effect of that is that the energy under the neutral case is lower than under the protonated case. The waters are the same energy, so those cancel out, but a protonated carbonyl is likely higher in energy than a neutral carbonyl. Now this energy gap is smaller, and that should make this overall barrier a little bit smaller because it pulls everything down, making that reaction a little bit easier to happen, thus a more reactive situation. Same idea under basic conditions, except what we're changing is the energy of the nucleophile. So the nucleophile is a higher energy now. It has a negative charge on that oxygen, so the pair of electrons is much less stable. And so overall that raises the energy of the reactants above that under the neutral case, where the water is going to be lower in energy and further down here. And so then overall you have the same thing again, a decrease of the overall change in energy of the reaction, either from here to intermediate or from here to product, and correspondingly and usually a difference in the activation energy as well. So what that really means is that the structure of our nucleophile and our electrophile can be used to judge the reversibility of a reaction and the equilibrium constant for an addition to a carbonyl. So an important reference point we want to keep in mind is that carbonyl, so carbon-oxygen double bonds, are overall more stable than two carbon-oxygen single bonds like this. And so because of that, the reference point is that this equilibrium favors the left, actually. So if you have water and a ketone, generally that reaction will favor the left side. However, of course, there are many different ways that this equilibrium can be perturbed, and so let's look at some of them. So if we're thinking about the structure of the electrophile, here's a table of 4 different electrophiles and the corresponding equilibrium constants. And so to walk you through here, the ketone has a very low equilibrium constant. That means the unhydrated form is much more favored, the left side of the reaction. An aldehyde, however, has an equilibrium constant close to 1, so it's about 50-50. Put some chlorines onto your aldehyde, that pushes the reaction equilibrium way to the right. Finally, if we're using this very strained ketone, that equilibrium favors the right even more. So some explanations for these trends are that first, what we'll see is that aldehydes are more electrophilic than ketones. So there are 2 explanations for this. The most common one that is used in introductory organic is that the aldehyde hydrate is less sterically congested because you have a hydrogen here instead of an alkyl group that you would have in a ketone. What that means is that in the hydrate product, there's just less sterics. And so if there's less sterics, that means overall the molecule should have a little bit less energy compared to a situation where there are steric interactions. It turns out that when people actually do in-depth computational analysis, what they find is the real explanation is in hyperconjugation. And what they find is that actually the ketone itself is more stable than an aldehyde. So we're starting off lower in energy here. That's a different argument from the first one, where I said that you end up at a different energy over here. This hyperconjugation looks like so, where what they're saying is that the carbonyl has a resonance form like this, with positive charge on carbon, and we can get a little bit of the neighboring CH bonds to delocalize into that empty or pseudo-empty p orbital on carbon in that resonance form. So that red arrow is the hyperconjugation interaction. So it's not conjugation because this is not a p orbital. It's hyperconjugation because this is a sigma bond. To be completely honest, as long as you keep in mind that aldehydes are more electrophilic than ketones, in terms of applying the concepts in these reactions, you'll be fine. But if you want to know why, then this gives you a little bit of thinking behind it. For the third example, where we have the trichloroaldehyde here, what we're seeing is that the chlorine inductive effect is destabilizing the resonance form in which we do have some positive charge on carbon. And so what we're seeing is that we're destabilizing the resonance form that is contributing to some of the stability of the molecule that increases the energy of our reactants to the point that it's higher in energy than the product for the hydrate. And so if that's the case, then the equilibrium should favor the hydrate. And that's what we see here in the experiment. Same idea in this strained cyclopropanone. The strain of an sp2 carbon is extremely high, and in a 3-membered ring that has an sp3 carbon at the vertex, that would be lower strain. So you're reducing a lot of that strain energy by forming the hydrate, and so then that becomes a much more downhill reaction overall. So that was all the electrophiles. Now let's think about the nucleophile structure. The way we want to think about nucleophiles in these reactions and in other reactions is that the strength of a nucleophile will correlate pretty well, but not exactly, with how basic it would be in an acid-base reaction. And so what that means is we're looking for things like negative charge and less electronegative atoms with negative charge on them. And here we'll look at some specific types of reactions. So the first one is a cyanohydrin formation, where cyanohydrin refers to a functional group where a nitrile and an alcohol are attached to the same carbon. In contrast to the hydrate formation we were just looking at, here the equilibrium favors the right side, even for a mundane ketone with no destabilizing effects on it. The reason for that is that the other reactant, our HCN, is a little bit higher in energy. And so on the basic reaction, what we're doing is we've increased the energy of our nucleophile to cause the overall activation energy to be smaller, and thus better be able to go over to the right, and in many cases be favored to the right, such as this one right here. A second important type of reaction is the formation of carbon-carbon bonds using ketones and aldehydes, and reacting those with what are called organometallic reagents. So an organometallic reagent is one in which a carbon is bonded to a metal, such as this phenyl lithium here. In such a reaction, we're getting the phenyl group as a nucleophile, attacking the aldehyde, forming overall phenyl carbon bond here. So let's look at the mechanism for this reaction. So because we're using a different type of nucleophile, it's worth drawing this one out. we have a sigma bond nucleophile now, sigma bond between the lithium and the phenyl ring. That is going to attack our carbon of the carbonyl, push electrons up, gets us to the product, or intermediate I should say, right here, tetrahedral intermediate. In this reaction, you'll notice I put in a step 1 in the reaction conditions and a step 2. And so whenever that is the case, and you see that in a reaction scheme, these are meant to be thought of as two discrete experimental processes. So first, I in the lab do step 1, and then I in the lab have to physically do something to initiate step 2. So we deal with step 1, draw out its mechanism. What happens then is you enter this point where this is the intermediate, and that's the only thing that's there in the reaction mixture. When I, as the experimentalist, think that this is the only thing in the reaction mixture and I'm ready to keep going, then I do step 2 and add some water to that reaction flask. What the water does is it allows us to protonate our alkoxide here, getting us to the alcohol, which we do want as our product. This type of a step is often called a workup step, where the workup is trying to say that we've done all the chemistry we want to do, and the workup is kind of cleaning everything up to be the isolated product. Almost always that's going to be an acid-base reaction that either puts in a missing hydrogen or removes an extra hydrogen. One final note about this reaction is that if you look at how I drew this, I indicated that a racemic mixture was formed in the products, and that is the case here. It's important to recognize that in this product, the carbon ends up having 4 different groups around it, and so there should be stereoisomers possible as products. What's happening is that this carbonyl, this aldehyde, has no difference between the face above the plane of the screen and the face below the plane of the screen. So just by random chance, our nucleophile is going to react half of the time from the top side, and then the other half of the nucleophiles will be reacting from the bottom face of the molecule. So then we should get a 50-50 mixture of the two enantiomers. One last reaction for us to look at. So this is the hydride as a nucleophile attacking a ketone or aldehyde, and what's called often just a reduction reaction. So what we'll say is that the ketone or aldehyde got reduced into an alcohol here. The reaction uses a special kind of a reagent called sodium borohydride. The idea here is that we need to put in a hydrogen as our nucleophile to get from the reactant electrophile to our product alcohol. To do that, you would imagine we need H- as my nucleophile. H- is referred to by organic chemists as hydride. It turns out that we can't ever use hydride as a nucleophile because it reacts much too quickly as a base. And so what you get if you mix hydride with the carbonyl is you actually deprotonate near the carbonyl, so like that, instead of doing nucleophilic attack. And so this is a concept to keep in mind for the future, which is that acid-base reactions tend to be much faster than our other mechanistic processes. So because we can't use hydride as a nucleophile, researchers invented sodium borohydride as a different way to have hydride nucleophiles. So the mechanism looks like this, where the sigma bond between boron and hydrogen are fairly nucleophilic, and that's what's attacking our electrophile, getting us to our alcohol like so. So in this reaction, you'll notice that I stuck in some solvent here. So this methanol is solvent. And the purpose here is that, well, first of all, these reactions are always done in methanol or similar alcohols. But secondly, that now we have a source of protons to do that acid-base reaction to get to the desired form of the product, which is also an alcohol. A mechanistic quirk of this reaction is that the byproduct of the borohydride part of the reaction is this molecule BH3, or borane. And borane itself is now a good electrophile because boron has only 6 electrons around it, so it has an unfilled p orbital. So then what happens is that we've actually made a good nucleophile as our tetrahedral intermediate here. And so often we'll get the reaction between the borane and the alkoxide tetrahedral intermediate. That then forms this species, which if you look at it is now again a borohydride. And so in this reaction what we find is that we can actually end up using all 4 of the hydrogens that were initially on the sodium borohydride reagent because that reagent kind of keeps turning back into a borohydride. So if we're thinking about molar equivalence, the minimum we really need would be 1/4 moles of sodium borohydride for 1 mole of carbonyl. One final comment I want to make about these last two reactions here is that I did not use equilibrium arrows here at all. The reason is that once you form this tetrahedral intermediate, this alkoxide species, this cannot go backwards. There's no way for our intermediate to collapse and kick out the original nucleophiles, the leaving group. The reason is that we're starting off with such high energy nucleophiles. So if we're thinking about the energy of the nucleophile, we're really way up here. And since we're way up here, it's much harder for a reaction to go backwards. And so these reactions are all essentially just forwards only. And we indicate that using just a one-directional arrow, like so. So that was a look at nucleophilic addition to carbonyls, specifically nucleophilic addition to ketones and aldehydes. We learned about how structure can affect the reactivity in these situations, so of both the nucleophile and the electrophile. And finally, we talked about several different types of reactions where different nucleophiles are used to create different types of molecules as products.